Okay, so in this example we have a little 4-bar mechanism, and we're told at the instant shown that link OA rotates counterclockwise about pin O with a constant angular speed omega OA, and that also at this instant links OA and BD are horizontal. And based on this information, we're asked to determine the angular acceleration of link AB and the angular acceleration of link, both AB and BD, pardon me for that. So as I try to do in all these problems, basically what we're going to do is we're going to work our way through the mechanism twice, once to determine all the angular velocities and a second time to determine all the angular accelerations. And the reason I'm going to do this is because we know in the computation of the angular accelerations we'll need the angular velocities. Okay, so to help us out and before we get going too far here, I'm going to define a little bit of geometry. I'm going to need throughout the point of this problem actually the distance, the horizontal distance if you would, between points A and B. And so I just want you to realize, because this is a right-hand triangle, this is going to be the square root of L squared minus D squared. And because I don't want to write that continually throughout this problem, let's just go ahead and call that the distance B. So by definition, we'll call that the distance little b. Alright, so once we have that in place, let's see if we can walk our way around this problem. So to start, I'm going to try to find the velocity of point A, given the velocity of point O. And so if I do that, I can say the velocity of point A is equal to the velocity of point O plus omega OA, a known quantity, crossed with the position vector of A with respect to O. If I do some substitution here, I'll have this is equal to 0. The velocity of point O is 0, of course, because it's a fixed point, plus omega OA in the k direction, crossed with r of A with respect to O, which is a distance L in the I. And so if I work this out, I know k cross I is going to give me j, so I'll have this is equal to omega OA times L in the j direction. Okay, now that I have that, I can work to point B, so I can say VB is equal to VA plus omega AB cross R of B with respect to A. And if I do a little substitution here, I know the velocity of point A is now omega OA L in the J, plus omega AB, unknown scalar but known direction in the K, cross with R of B with respect to A, which we just said was a distance little b in the I, plus D in the J. If I expand the right-hand side of this expression, I'll have omega OA times L in the J. And K cross I gives me a J, so I'll have plus omega AB times little b in the J. And then K cross J gives me minus I, so I'll have minus omega AB times D in the I direction. Now what I'm going to do is I'm going to say, well, but we also know that VB is equal to, in this case, the velocity of point D plus the omega of bar BD crossed with the position vector R of B with respect to D. If I do a little substitution here, we know the velocity of point D is 0 because it's a fixed point. I'll add to that the unknown omega BD, which will be in the plus or minus K, and I'll cross that with R of B with respect to D, which is minus L in the I direction. If I expand this cross product, K cross I gives me J, and so I'll have minus omega BD times L in the J direction. Now if we look at the last two results here, what we've recovered is two different expressions for VB, and so I know I can equate those. And so if I choose to equate these two lines of my math, what I'm going to get here is that omega OA times L in the J plus omega AB times little b in the J minus omega AB times little d in the I has to equal minus omega BD times L in the J. Well, I know that a scalar equation can be related to different vector equations, and so the way I'm going to do this is I'll pull out terms. And so if I pull out those terms, what am I going to end up with here? Well, if I look in the I direction, I'm going to have that minus omega AB times D has to equal 0, which of course tells me that omega AB is going to equal 0. Of course, this will only be true at the instant where the geometry is shown as given in this problem. I can then do something similar with J, and if I look at the J term, I'll have that omega OA times L plus omega AB times B is going to equal minus omega BD times L. We've just shown in the previous step that omega AB equals 0, so this middle term will go away. I can then cancel out the L's on each term, and what I'm going to get here is quite simply that omega BD is going to equal minus omega OA, and if I want to write that in vector form, I can append a k. Great, I now have expressions for the angular velocities associated with this mechanism, and then given this piece of information, I can now go ahead and proceed with some angular accelerations. So let me add a new page here in my solution, and then drift back up a little bit. So pardon me here as I pan up on the page. So now what I'm going to do is I'm going to essentially replicate what I've done before, and so if I go back to the figure, let me go back to the beginning of this problem. I can work my way around this mechanism now, starting at point O, going to point A, and proceeding through. Again, in this case, using acceleration terms. So if I do that, and I'll start again here on the bottom page, I can say that the acceleration of point A is going to equal the acceleration of point O plus the angular acceleration of bar AO cross r of A with respect to O. And because this is a scalar problem, subtract off omega AO quantity squared times r of A with respect to O. If I do some substitution here, I know the acceleration of point O is going to be 0. We're told in the problem that omega OA is a constant rotation rate, so the second term in this equation is also going to give me 0. And then I'm going to subtract off the known value omega OA squared times r of A with respect to O, which is simply L in the I direction. And so that means my final acceleration of point A will simply be minus omega AO squared times L in the I. Now that we have that, we can go up to point B, and so if I do that, I can say that the acceleration of point B is going to equal the acceleration of point A plus alpha BA cross r of B with respect to A. And then because this is a scalar problem, I can subtract off omega AB quantity squared times r of B with respect to A. Pardon me, let me fix my hat here a little bit for you. So if I go ahead and do some substitution here, we've just shown that the acceleration of point A is minus omega AO quantity squared times L in the I. I'm going to add to that alpha BA, unknown quantity in the K, and I'll cross that with the position vector B with respect to A, which is little b in the I, plus the distance, I believe we called it D, in the J. And then I'm going to subtract off of that omega AB squared, but keeping in mind omega AB 0, we know the last term goes to 0. So if I go ahead and expand the right-hand side, we'll have that the acceleration of point B is minus omega AO quantity squared times L in the I. K cross I gives me J, so I'll have plus alpha BA times B in the J. And then K cross J gives me minus I, so I'll have minus alpha BA times D in the I direction. I can then solve for the acceleration of point B using point D, and so I can say the acceleration of B is equal to the acceleration of D plus the angular acceleration of length BD, cross with the position vector B with respect to D, and then subtract off omega BD quantity squared times r of B with respect to D. If I expand this, again D is a fixed point, so it'll have 0 acceleration. Alpha BD is an unknown, in fact that's one of the things we're asked to find, and I'll need to cross that with r of B with respect to D, which will be minus L in the I. And then I'll subtract off that omega BD squared, which I know is simply going to be omega OA squared, the square will make the sign go away, times r of B with respect to D, which is minus L in the I. If I expand the right-hand side of this equation, I'll end up with K cross I gives me a J, so I'll have minus alpha BD times L in the J, and then minus the minus is going to give me a plus, so I'll have plus omega OA quantity squared times L in the I. As we did with velocity here, it's important to be cognizant of the fact we have two different expressions for the same thing, namely the acceleration of point B, so I can equate those. And if I do that from the first expression, I'll have minus omega OA quantity squared times L in the I plus alpha BA times little b in the J minus alpha BA times little d in the I has to equal minus alpha BD times L in the J plus omega OA quantity squared times L in the I. Again, a vector equation in two-dimensional space is, of course, two scalar equations, so if I pull out the I component of this, I'll have minus omega AO squared times L, minus alpha BA times D has to equal omega BA quantity squared times L. And if I pull out the J components, I'll have alpha BA times B is equal to minus alpha BD times L. From here you can quickly realize we have two equations and two unknowns, with those unknowns being what we're asked for in the problem, namely the angular acceleration of link BA, which will be the scalar quantity you solved for, appending the K, and the angular acceleration of link BD, which if you go ahead and substitute will be recovered by appending the K. Alright, from here it's just plugging in numbers and running through everything. I know you can do that. Best of luck.